We're going to be talking about organic chemistry and biochemistry this week and next. Now, organic chemistry is a study of compounds of carbon. These compounds might contain hydrogen, oxygen, nitrogen, and sometimes sulfur, phosphorus, and halogens. Halogens are in group 17, and these are your fluorine, chlorine, bromine, or iodine. Now, organic chemistry has over 10 million organic compounds, and we're constantly finding new ones each year. By contrast, we've only found 1.7 million inorganic. Inorganic compounds are those that don't have carbon in them. So, approximately 85% of all known compounds are organic. There's a huge link to biochemistry with our carbohydrates, lipids, proteins, enzymes, nucleic acids, hormones, vitamins, and almost all other chemicals that live in living systems. There are several functional groups which will be important for you to identify. Aldehydes, you're going to see this structure. And carbohydrates tend to be your aldehydes. You have amides, which have the double bond here, the carbonyl group, the carbon double bonded to the oxygen with the nitrogen and the hydrogen. Your proteins have a lot of amides in them. Aminos are this functional group, and they're found in amino acids and proteins. Your carbonyl group you find in ketones, aldehydes, carboxylic acids, and amides. Carboxylic acids are in your amino acids, proteins, fatty acids. Esters have an oxygen in the center, and it connects to a carbonyl group with an alkyl group and another alkyl group. An alkyl group is a carbon chain. You have ethers, which is just that oxygen connecting to alkyl groups. And you find these in your disaccharides, polysaccharides, and lipids. Hydroxyls, your alcohols have those, monosaccharides, amino acids, and nucleic acids. Your ketones are in carbohydrates, methyl groups, right here. Your phosphate groups you're going to find in your phospholipids, your ATP and nucleic acid, and your sulfhydryl groups. The main ones, I'd say ketones and aldehydes and carboxylic acids and hydroxyl groups and ethers. You should be able to recognize them, but especially these five. Now, hydrogen bonding helps in DNA with binding to enzyme substrates as well as complementary base pairing. So we're going to talk a little bit more about complementary base pairing, but that is how our double helix is created in our DNA. Hydrogen bonding allows for this double helix structure of the DNA to occur. You can see here that with the oxygen and the hydrogen here, that they have that hydrogen bond and it pairs them. And it helps provide that double helix structure. Now, if we were going to compare organic and inorganic compounds and their properties, it's important to note that in organic compounds, it's primarily covalent, When in inorganic compounds, those are your ionic bonds. Because ionic bonds are stronger, most inorganic compounds are solids and they have high melting and boiling points. They also are soluble in water because they dissociate into charges. Almost all are insoluble in organic solvents then. So oil and water won't mix, for example. Aqueous solutions will form ions that conduct electricity. Very few of them burn, and the reactions are often really, really fast. In contrast, with the covalent bonding in organic compounds, many are gases or liquids or solids that have low melting points. They're insoluble in water, but they'll dissolve in organic solvents. Remember the saying, like dissolves like? This is where that comes into play. They won't conduct electricity because they don't separate into charges, and almost all burn or decompose. This is where all of our fuels come from. They're organic compounds, and the reactions are typically very slow. Now, alkanes are hydrocarbons that contain only carbon-carbon single bonds. The simplest alkane is methane here, and followed by ethane. So this is the smallest alkane, and you have your second smallest here with 2 carbons. Now, alkanes have the ending ane, and they only have single bonds in them. An alkyl group, as I mentioned, going over the functional groups, it's just a substituent group derived from an alkane by removing the hydrogen atom. So, for example, we have methane, which is CH4. Methane, we remove a hydrogen and it becomes methyl. It's an alkyl group. You just drop the ane and add il. Ethane becomes ethyl. Propane becomes propyl. Propane becomes isopropyl. Butane becomes butyl. Isobutyl or isobutane becomes butyl. Secbutane becomes secbutyl, and terpbutane becomes terpbutyl. So all we're doing is dropping the ane and adding the suffix il. There are 3 ways of showing the structures. The first is the expanded formula. So you draw everything out so that you could see all the connections between every single element. The condensed formula, you just draw the main chain. And then the alkyl groups, you can draw condensed. Or you could draw the skeletal structure. The skeletal structure here, it's understood that where they meet, that has a carbon there. That has a carbon. At each point, there are carbons. And attached to those carbons, you would have the hydrogens attached until the carbons had 4 bonds. So you'd have your H here, your 3 hydrogens here. This just gives you the basic structure, and you fill in everything else in your mind. So you can see the vast differences between them. Here we have are alkanes and our molecular formulas. So methane is CH4, ethane is C2H6, propane is C3H8, butane is C4H10, pentane C5H12, and you can see methane only has one, ethane has two, propane has three, butane has four, and then you might be recognizing some of the prefixes at this point. Pentane, penta means five, hexane, hexa means six, heptane means seven, hepta, octa, eight, nona, nine, decane, 10, and then you have like tetradecane, so 4, 10, 4 and 10, tetradecane, octadecane, 18. So you will be able to make some similarities with the prefixes. They're slightly different from our binary compound prefixes, but you do have those similarities. Now, for nomenclature, if we're going to name an alkane, we first find the longest chain in the carbon of the carbon atoms. So, does it have 5? It would be pentane. Does it have 6? It would be hexane. Does it have 7? It would be heptane. And then you number the carbon atoms by counting from the end of the chain nearest to the substituents. So, for example, if we had something like this, and this had CH3 on it, this alkyl group is a substituent. I would name it 1 because the substituent is closest to the edge. 2, 3, 4, 5. So I'd name my carbon or number my carbons depending on where the alkyl group is closest to which end. Then we add prefixes to the name of the longest chain to indicate the names of the substituents. Then we identify the position of a substituent of branch by the number of the carbon atom that it's bonded to in the chain. And then we have if we have multiple substituents, they're going to be named individually and placed in alphabetical order at the front of the name. So this one, for example, is 1, 2, 3, 4, 5. This is going to be pentane because it's all single bonds. But here on the second carbon, I have my methyl group, CH3. So it would be 2-methyl pentane. That would be the name of this compound. We have a few more things here. We have our methyl, our ethyls, and-propyl, so that you could see the structures, and butyl, butyl, isobutyl, and tert-butyl, what they look like. So if we look at this, we have propane here. It has, just for practice, we have 1, 2, 3 carbons. That's it. So its name is propane. Here we have 1, 2, 3. So that would be propane, which is what we put here. And on 1, 2, so on the second carbon, we have 2-chloro because we have a chlorine. We don't write 2-chlorine propane, we say 2-chloropropane. Here we have our propane again. 1, 2, 3. So we write propane. On the second carbon, we have a methyl group. So it's 2-methylpropane. This one, we count 1, 2, 3, 4, 5, 6 carbons. So that's hexane. And on the second carbon, we have a fluorine. And on the fourth one, we have a fluorine. So this is 2,4-di, or prefix of 2, 2,4-difluorohexane. Here we have 1, 2, 3, 4, 5, 6 carbons. That's hexane. So that's where the hexane comes from. You got to kind of write the chain first and then the constituents, the substituents. On the first carbon, we've got bromine. So it's 1-bromo. And then on the third carbon, we have chlorine. 1-bromo, 3-chlorohexane. So if we were going to answer this question, we'd look here and we'd count 1, 2, 3, 4, 5, 6, 7, 8. So this is octane. Remember, you count from whichever end this is closest to, and it's closer to 1. So this is 4 because it's on the fourth carbon. 1, 2, 3. This alkyl group has 3 carbons, which is propyl. So it's 4-propyl octane. I want you to try answering these questions and then come back and we'll go through them and see if you got it correct. So if we look at this, what is the correct IUPAC name for the compound shown below? Well, we have 1, 2 carbons, so that's going to be ethane. But I notice that the substituent is always on the first. It's the closest. So I numbered them incorrectly. This should be 1 and 2. So since I have a substituent on my first carbon, it's going to be 1-fluoro, because it's a fluorine, fluoroethene, which is right here. For this second one, what's the correct name? Well, let's count. 1, 2, 3, 4, 5, 6, 7, 8. Remember, each point represents a C in the skeletal system. There are 8 here, so this is going to be octane. Now, which side should we start counting from? We start from this one. 1, 2, 3, because this substituent is closer to the beginning. So this is going to be 3 methyl. And then we come here, 3, 4 ethane. But I can't write it as 3 methyl 4 ethane because I'm supposed to write it in alphabetical order. So I have to correct it because if you have more than one substituent, you write it in alphabetical order. So I write 4-ethane, 3, or sorry, not ethane, ethyl, 4-ethyl, 3-methyl octane. Here we are. If you guys have questions, let me know, and I'm happy to help. We'll see you next time.